Greetings. Recently I posted a video describing two types of hum that you might find in an amplifier. 60 cycle, generally associated with tubes, and 120 cycle associated with filter capacitors. Shortly after I posted the video, a subscriber sent me a message and asked, how can 120 cycle hum occur? I mean, where does the 120 cycle current come from? So I thought I'd post this short and hopefully to the point video to explain how it happens. To go into that, we first have to discuss a little bit about how rectification occurs in an amplifier. Now there's several ways to rectify the alternating current. One is to use a single diode. And diodes are peculiar little electronic devices that only allow current to move in one direction. So here, as long as the current is positive, it allows the current to flow through the diode. And then when it tries to go in a negative direction, it eliminates it. The next time we encounter a positive type of wave, we allow it to pass. So you'll end up with, if you put in 120 volts at 60 cycles, end up with about 60 volts, about half of your voltage, because let's face it, half of the voltage was eliminated, and at about 60 cycles. Okay, now this would not be very useful in an amplifier because it would really produce hum that would almost be like a machine gun. You can imagine as each one of these waves hits, you're going to get a kind of a pop, 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 pop sound. It can be smoothed out, but it's very difficult. I think you'll understand the smoothing process a little better in a second. Let's look at the way most amplifiers are made, and that is with our 120 volt 60 cycle input alternating current, we can run it through what we call a full wave rectifier. Now there's two different types of full wave rectifiers. We can use 2 diodes or a tube, or 4 diodes, and that is called a bridge. Don't be worried right now if this doesn't make much sense. I will explain it in just a second. Now what happens is that with 2 diodes, we have them arranged in such a way that we allow this part of the wave to pass, and we allow this part of the wave to pass, but we invert it and make it positive. So where we have 1, 2, 3, 4 peaks, 2 on top, above, and 2 below the central axis. Over here we will have all 4 peaks above, and we can say, and this is all rather simplistic, we can say that they're all plus. So this is all positive now. Negative is gone. Now if we arrange the diodes in a different direction, if we reverse them, we would have all of the humps down below, and we would have negative direct current instead of positive direct current. In almost every amplifier I've ever seen, it's always they're arranged so that it's positive, like this. Now, as you can see, we have twice as many humps above the central axis. So now, instead of 60 cycle, we have 120 cycles per second. There's 120 of these little humps that will pass by every second. It's still around 120 volts. We did not lose half of our voltage. We have it all. Again, this is rather simplistic, but it is at 120 cycles per second now. And we have an area in between the humps where the voltage drops off and then comes back, and this is called ripple, and this will make the 120 cycle hum. If this ripple is not eliminated, this is almost like, if you watch, sort of like a alternating current wave up here involving the peaks and the lower areas down here, the intersections, so that we have a varying alternating current which makes that hum, that kind of hum that you might hear if your filter capacitors have failed. Now, filter capacitors act sort of like that backup battery you have on your computer, or say in a hospital operating room if they have a power failure. The battery takes over and starts to provide the voltage that's needed to keep things going. Well, that's exactly what happens with your filter capacitors. Down here, as the voltage is peaking, it's charging the filter capacitor that's attached to this line. Then, as the voltage peaks and starts to drop off, the filter capacitor says, oh my Lord, look, the voltage is dropping, I'd better discharge and fill in that gap. So we have a power failure here. The the capacitor fills the gap, then it charges the capacitor again, it fills the gap as the voltage drops off, charges over here, fills the gap, and you see that instead of having this very jagged ripple that gives us the 120 cycle hum, we have a fairly smooth waveform here that provides uniform high voltage for our amplifier and without any hum that you can hear. Now, if your filter capacitors are failing, if they're old or dried out, these are the electrolytic capacitors, we will not have this discharge to fill the gap, and we will have 120 cycle hum, which you will hear from your speaker. Now, while we're speaking about diode and tube rectification and also bridge, let's take a look down here at two possible ways to do that. Number one, we'll have the full wave rectifier where this is going to be our power transformer. This is our primary 120 volt winding. Here's our secondary winding. Now, one catch, if you're going to use diodes or a tube to do your rectification, you have to have a center tapped secondary on your transformer. And all it takes is the two diodes. Now I'm going to show you how the tubes contain diodes. We'll see that in just a minute. But for now, you'll see that each of the output wires from the secondary has a diode, and we end up with a B+ direct current coming out here that will go to the filter capacitors to be smoothed out. Now in the bridge rectifier we have 4 diodes, and they're arranged in this rather unusual pattern here, and the end result, first, we don't need to have a center tap on our secondary of our power transformer, so the transformer can be a little cheaper. We end up with our B+ coming out here. This is our direct current, positive, and we have our negative down below. This is generally grounded at this end. Now, what's the advantage of the bridge rectifier? You end up with a little more voltage, a little more current, and you don't need the center tap on the power transformer. So it's a little better. Okay, it's a little superior definitely to this method. Now, I've made a drawing here of the two different types of rectifier tube that you're probably going to find in your guitar amplifier if it is tube rectified. This is the typical 5Y3, 5U4, 5Z3 in the really old amps, 5R4. I've seen 6AX4s, 6AX5s, and some little more recent amps, probably from the late 60s. Now notice it has here a heater, and this is what's glowing when you look in at the tube, is this. And when it gets hot, the electrons boil off of it and come here to the plates. The plates are positively charged, so the electrons are attracted to them. The electrons are only going to go in one direction. If they're heated and driven off from here, and this is positively charged, they're only going to go this way. So what we have in this type of tube is 2 diodes. 1 diode, 2 diodes. Now the other and actually better way to make a rectifier tube, and this will be the 5V4, 5AR4, 6CA4, and GZ34, my favorite, you have a cathode. Notice that here we have no cathode, over here we do. Now what happens here is the emission from the cathode is secondary. We're going to heat it up, but the electrons are not going to go from here to the plates. Instead, we're going to, this is like turning the burner on the stove and setting a pan on it. The cathode is heated by the heater filament, and then once it gets hot enough, it boils off electrons that will go to the plates. Again, they only travel in one direction, and there's 2 diodes within the tube. But because there is time between turning on the tube and the release of electrons, This type of tube has what we call a slow startup. And that is, once you flip the on switch onto your amp, there's not an immediate rush of high voltage to your amplification tubes. Instead, the heater will heat up and then in turn heat the cathode, and then the cathode will slowly, just like water boiling on the stove, slowly start to release electrons to the plates. This is much gentler on your amplification tubes and makes them last a lot longer. This is why these tubes are superior to these tubes. Now let's take a look at a 5U4 tube, and I think as you look in you'll see the two diodes that are present in the tube. We have two separate plates and filaments. The filaments are down here below. They're within these kind of gray metal surrounding wrappings, and that's over here. This is the filament that heats up. And these are the plates, the grayish metal plates that are up here, and then each of these then is a diode. Now this is a full wave bridge rectifier. This is used in a lot of computer equipment and things of that sort. The alternating current connections are made to these two diagonal corners. It would be to this and this wire. Then the positive output has the corner beveled and a plus, so this will be your B plus, your high voltage that is positive, and down here is the negative. This will be your high voltage that is negative. Now here we have a computer power supply with 4 diodes arranged in a full wave bridge configuration. Notice that there's a silver band at the end of the diode. This is the way diodes, their polarity is indicated. That band corresponds to this line. So if you're using diodes in your circuits, you have to be sure that the diode is in the right direction, with the band in this case would be on the right hand side of the diode. Now these 4 then will rectify the high voltage for the power supply. There'll be a ripple in that output voltage, and that will be smoothed by these 2 electrolytic capacitors. Okay, that's about it for this video. I hope everything made sense. And for those of you who didn't know much about how rectifier tubes function or how power supplies work, I hope that this filled in some of the gaps, just like the electrolytic capacitors do. And then I eliminated some of your ripple. Okay, so please stay tuned for future videos. I haven't turned up any old amps lately, but when I do, you'll be the first to know. Okay, I hope to see you soon. Thanks for watching.